Okay, let's begin. So in the last class, we kind of started to see how we can make an op-amp, and in the process, the first circuit we came up with was the differential amplifier, which looks like this. So V1, V2, and let's say take the output from here. Okay, so what was this source voltage? If the it was basically the average of the two, right? So initially we'll assume R naught to be infinity. So if that is the case, you know that the incremental current flowing here is Gm of the transistor times the gate to source voltage, which was basically Gm times V1 minus V2 by 2. And you know that in a small signal, the current source is an open. So this current I1 has to flow here, and that generates the output voltage, which is I1 times RD, and that gave the gain to be Gm RD by 2 times V1 minus V2, right? Great. And I'm sure you guys might be familiar that if you have any two voltages, you can decompose them in this form: V1 plus V2 by 2 plus V1 minus V2 by 2. And how will I write the next one? Minus V2 by 2 is a simple algebra. But okay, so what is this portion called? It's the common mode or the average of the two, right? So this is basically, I'll call delta V IC for the common mode. And this guy, it's a differential mode, right? So, I mean, of course, there's a reason we do it. First is obviously we want the op-amp only to respond to the difference between the two signals, right? We want it to respond only to the differential input. And secondly, if you have symmetric circuits like what we have here, it turns out it's much easier to analyze the circuit for these two cases of inputs, right? So we'll see that quickly. So this is the diffamp. Let me draw it again. So let us say now I consider differential input. So this is delta VID by 2 and minus delta VID by 2. So that the differential input I apply is delta VID, right? So if that is the case, what can you say about this source node? It's at 0. I mean, we already saw it's the average of the two, it's 0. But even if not, if we have, let's say, a linear network. Okay, so let's say this is terminal 1 and terminal 2. I take a mirror image, right? Basically, I flip it like this, the same network. So which means the terminal 2 comes here and 1 comes here. So here I apply the inputs and say connect the nodes here. If I apply Vi and minus Vi, what can you say about? What can you say about this node? Huh? Why is it 0? Okay, yeah, symmetrical. So what happens? Huh?
Voltage across the two systems will be same.
Voltage across it. What do you mean by voltage across the two systems?
It is difference I'm asking.
Voltage difference. I mean, what are the two voltages are you referring to?
So I'm referring to the two input and output data.
This one.
Yeah.
Okay, I mean, let's say I call it Vx here again.
Yeah. So I'm Vx and that Vd I'm referring to. Vx and Vd.
No, I mean, there is only Vi here and minus Vi here. So what Vd are you talking about? Okay, I mean, see, this is a linear network. I have two inputs. How will I analyze it? Superposition, right? And of course, if you want to find the how Vi here contributes to Vx, so it's a linear network. So Vx will be some k times Vi. Fine. Now, let's say you want to find the transfer function from this guy to here. What will be the transfer function? Yeah, I mean, transfer function is still k. The input is minus Vi, so it's minus Vi times k. It's 0, right? Okay. So it comes out because of linearity and the fact that you have two identical networks. So which means all the nodes which are at the symmetry, line of symmetry, they will be at 0. And of course for small signals, this is also a linear network. So this is the line of symmetry. So this node here, that will be at 0, right? And this lets us, this makes the analysis easy, right? So now, since this is at 0, I am interested in finding V out. I can consider only one half of the circuit and say I take the right half. I'll label the transistors M1, M2. So I will probably write it here. Yeah, write it here maybe. So now the half circuit will look like this. Vx is 0, so this is ground. So this is V out, and this is minus delta VAD by 2, right? And of course, this is a common source amplifier. So what is the gain of this? Minus GM times RD. So into the input, this is the output. So that's what you get again, right? So of course, this is with respect to having a differential input. So this is called the differential half circuit. Now if you have a differential half circuit, you can also have a common mode version. So let's say I apply the same incremental input to both the terminals. Okay. So what can you say about the drain voltages here? So it's, remember this symmetric, I mean the same network is copied and pasted, right? I'm applying the same incremental voltage to both the gates. So what can you say about the drain voltages here? They will be same. So if they are same, basically I can simply short them, nothing is going to change. So which means the circuit again reduces, right? So here I had a resistor RD and a resistor RD. Seems like they are getting shorted. So what is the effective resistance you have? Yeah, that's exactly what I asked before, right? So why is it, both will be at same potential, right? See. No, okay, see, okay, that's why I wrote in a different color. The input we apply is delta VIC and plus delta VIC, the same input. We are applying the same input, so that's why both of them are at the same potential. So which means basically I can short them, nothing is going to change in the world. So which means the circuit now reduces to this, where I have a resistor RD by 2, and what you see, you have this transistor M1 and M2. Their gates are already at the same potential, sources at the same potential, and I am saying we can also short the drain now. So it looks like the two transistors are put in parallel. So it's going to look like this. So if the individual transistors had an aspect ratio W by L, what will be the aspect ratio for this one? Twice. Okay, and then you have the current source here. Use the same color. This is delta VIC and this is V. And this guy is called the common mode half circuit. Okay, why is ID by 2? Why should be ID by 2? No, both RDs are in parallel, but the current source, I mean, we are doing nothing to the current source, right? It's like we have two branches, current source is common. The two branches are basically, overlapping with each other, and the current source remains same. Okay, See, what will happen is if you, and this you can basically, sorry, this is RD by 2, I'm sorry. Is this what you mentioned? Yeah, sorry, I made a mistake. Is it fine? Great. So now let's say I apply this increment in the gate here. What will be the increment in the output voltage? Why? Yeah, so basically you see that the transistor is biased with a constant current. So the current is always going to be same. So whatever you do at the gate, the output voltage is not going to change, right? So the gain here for the common mode signal, which will be called the common mode gain, is 0, and whereas this guy is the differential mode gain, right? GMRD by 2. This is GMRD by 2 times delta VID, and this is the differential mode gain. Fine. Great. So let's take this guy again. Okay. So at the end of the last class, as I was saying, so on ICs, most of the time the biasing is done with a fixed current source, right? And the reason, one of the reasons is because it's much easier to copy and replicate currents than replicating voltages. And for replicating currents, you can do this guy. So you take a current I0, pass it through a transistor, put it in feedback like this, so that you obtain the required gate voltage to support the particular current, and then you can basically copy it to how many ever transistors you want. And you can also play with the sizes of the transistors to get scaled versions of the current, right? And this is the current mirror, right? So now basically you can replace this current source by this guy, so you can do this connection now. So now we have a complete transistor level implementation, right? So what is the output impedance of this guy if I call the transistor M1 and M0? R0 of the transistor, that's all, right? Okay, because incrementally the gate is at ground. I mean, if you make any changes to the gate, sorry, to the drain, no change will be reflected at the gate. So gate is at ground, source is at ground incrementally. So the only thing you have in the incremental picture is the R0 of the transistor, and that's what you get. Okay, but if you have an ideal current source, what is the output resistance? Infinite. So of course, in many times you might want to make this current source more and more close to ideal. That is, we want to make this output resistance as high as possible. And one way to do that is to, take this guy. So this is the ordinary current source. To make it a better current source, what we do, we try to put a current buffer so that the buffer takes care of delivering the current to whatever load you want. And the simplest buffer we know is, let me make some space here. The simplest current buffer we know is the common gate. So it will look like this. Okay. Of course, this is only in the incremental picture. We'll have to connect it to some bias voltage here finally. And this is M1, M2. So I had asked you guys to work out what is the output resistance. So what was it? Okay, R0.
R0 plus 1 plus mu into.
Okay, the transistors are labeled like this, right? What did you get? Okay. Anyone?
Intrinsic gain of M2 times the R0 of M1.
Okay, that's the approximate version. What is the complete expression?
But I got sir, but I took like M1 and 2
Li-
same. I take
Oh, okay. I
That's why
mean,
I
yeah,
got the
understood.
factor of 2.
Yeah. So this is the exact expression. So I mean, it's easy to remember, right? So the first term is whatever resistance you have down. The second term is basically the R naught of the transistor you have here, plus the intrinsic gain of this guy times whatever resistance you have here at the bottom. So, and in most of the times you will find that the third term will be the dominating factor. So you can basically approximate it as Gm2 R02 times R01. So basically it looks like whatever resistance you have here at the bottom, that seems to be multiplied by the intrinsic gain of the transistor you put up, and that's how you get a higher output resistance. Okay, great. Oops, sorry, made a mistake here. So not just this, if you have a case like this, so let's say this is some Rx and this is say some M1, what will be the output resistance now? It's same thing, right? I mean, instead of having this M1, which is basically a resistance of R01 in small signal, I have a proper resistor Rx. So there is no change. So this is still, approximately Rx times the intrinsic gain of this guy. Okay, that's fine. And yeah, I'm sure you guys know the name of this configuration. So this is the cascode. Is that okay?
So what is the gate of the M2? Not there.
Here.
The cascode.
That is connected to some bias voltage. Incrementally it should be short. It's a common gate. So incrementally the gate should be short, but you will have to bias it so that it remains in saturation. Great. So now you kind of know how to implement everything in this diffamp. So the next step is obviously to try to make this guy better and better. So we know that the differential gain is what here? What is the gain? GM RD by 2, okay, times V1 minus V2. Sorry, this is not the gain. Gain is just this. So ideally you want this gain to be as large as possible. So you can either increase GM, increase RD, or do both. So for increasing GM, what all you can do? What all can you do? Yeah, you can basically increase the current or increase the aspect ratio of the transistor. But beyond some point, you might not be able to increase current or sizes. So let's say your this is at the maximum, it can for now. So the next step is to try and increase RD, right? So of course, if I keep increasing RD, I'll have higher and higher gains. But what is one problem that you foresee?
Space.
Okay, forget about space. Let's say, I give you free space. What else? We don't know about noise. Okay, assume that we are in operating at 0 Kelvin, no noise. Yeah, we are increasing resistance. So what is the problem?
Power dissipation.
Okay, power dissipation. Okay, is there something more fundamental that prevents you from doing it? See, if you have this guy, right? So if I call this say VD2, what is the operating point voltage for this drain? So first of all, what is the current in the two transistors? Operating point current? I0 by 2. We have a current I0. We have two symmetric branches. It will obviously split equally. And if the supply is VDD, what is the drain voltage? It's VDD minus the drop across the resistor RD, that is I0 by 2 times RD. Okay. So now if I keep increasing RD, what happens? VD2 will start to decrease, right? And obviously, you need to retain this guy in saturation region. So which means I'll have to start to increase VDD, and that's obviously not possible. Okay. So this is a limitation if you keep increasing RD directly. Okay. So let me just show it using a graph so that you can understand the solution quickly. So let's say I plot the IV characteristics of this resistor RD. Okay, and I'm saying RD is very, very large. So how will this IV characteristic look like? Yeah, it's a resistor straight line, but if the resistor is very, very large, in which direction the characteristic tilt to? Towards the whether this is the correct thing. Sorry. Whether it will look like this or look like this. Let's say this is 1, 2. Second one, okay. So I'll have to do 2 times undo. So too much. So this is how the IV characteristic will look like, right? Now, I mean, if let us say you are trying to bias it at some current I0 by 2. You see that the corresponding voltage drop across the resistor is quite large. This is basically the same problem we saw. Okay, but that's when people realized that all you need is that the incremental gain or the small signal gain must be very large. So which means you need to have a large small signal resistance, right? That's all you want. So you don't need to actually have a physical resistor which acts like a resistor all the time. You can have a device that acts like a large small signal resistor like this. Okay, and then of course the characteristic must pass to the origin. So you can do this. So in this region you see that what is the resistance? Infinite, right? So you get an infinite resistance if you operate in this region. But now you see that if you try to bias it at a current I0 by 2, the voltage drop is quite minimal, right? Is that fine? So do you know a device which has an IV characteristic like this? It's a MOSFET. So what you can do, you can basically go ahead and replace this guy with a MOSFET. Okay. So now let me label these guys M1, M2, M3 and M4. Okay. So this is the motivation behind using active devices at the load side. Okay. So now let us say this is the circuit we have, and I am looking at the differential case. So this is delta V by 2.
If you operate at this current, the current
Right.
It is in the trial region, so the resistance will be very small. Right?
Yeah, I understand, but I just gave you a rough idea, right? But you can always have a transistor which does this, and you can have small. Yeah, what you told is absolutely right. I think I should have been more careful. So if MOSFET you can get nice characteristics like this. So even if you have operating, I mean, even if I0 by 2 is here, you'll still have a much smaller voltage drop. Okay. Thanks. Yeah. Cool. So so if this is the circuit now, and I'm applying a differential input, first tell me what is this source voltage? It will be at 0. So what will be the if I call this as the output now? What is the incremental output? Let's assume R0 for all transistors. There is no RD. So first of all, what is the incremental current flowing in the transistors? Okay, first let's quickly draw the half circuit, right? So let me draw the right half. So you have M4, M2, And then what happens to the source? It's a differential half circuit. Huh? Come on guys, so we just saw, right? I'm saying that one side I'm applying plus delta V by 2, other side it's minus delta V by 2. So what will happen to this common source voltage? That will be ground. This is the thing. So here I have minus delta V by 2 and this I call as V out. And these are transistors M2 and M4. So what is the gain here? GM2?
Resistance of the transistor and
Like R0 2
Mhm.
R0 4 into G.
Yeah, right. So I mean the incremental current flowing is what? GM times the gate source voltage, so that's minus delta V by 2. This is the current. I mean, if you were to draw the small signal equivalent, so from drain to source you will have a current GM VGS. You will have R0 of the transistor, and similarly for M4 you see that gate is at incremental ground, source is also at incremental ground, so it will just have R0 of this guy, which is ground. So the voltage here is minus GM VGS times the resistance you have. So V out is basically not 4, right? And that's basically GM delta V by 2. I mean, this is same as the common source amplifier, right? There is no difference. Okay. Is that okay? So now, of course, you since R0 can be much larger, you can get a much higher gain. Okay, great. So here everything is set. The only thing pending is how to generate this gate voltage. Remember, this should be at incremental ground like this, but we need to connect it to some DC bias voltage so that the transistor operates in saturation, right? So let's quickly figure out how we can do that. So we'll redraw the circuit here once. So let's say M1, M2, 4. So here I will have to generate this gate voltage, and remember if I call the current I0, what is the current flowing through the transistor M3? It's I0 by 2, right? Operating point current is I0 by 2. So all I need to do is generate a gate voltage for this transistor so that it carries an operating point current of I0 by 2, right? And one easy way to do it is basically take, say, current I0 by 2, pass it through an identical PMOS transistor, put it in feedback like this. That will, with this you can get the required gate voltage to carry the current, and then you can connect it. Fine. So I'm saying this is one way to obtain this gate voltage, right? So we notice that the current through the transistor M3 is I0 by 2 in DC, right? So what I take is, let's say you have a current source of I0 by 2, pass it through an identical PMOS transistor, put it in feedback like this. So that will obtain you the required gate voltage so that the transistor will carry the current of I0 by 2. And then you can basically connect that gate to this. So, and this is again a current mirror, right? So you have current here and you are basically copying this current to this branch, that's all. Okay, is that fine? Great. So now if you notice, okay, let me mark it here, maybe I0 by 2. Okay. So if you notice, you actually don't need to have a separate branch like this. So if you think about it, this branch, all it requires is a current I0 by 2 and a PMOS transistor. So if I see, in this branch the current is I0 by 2 and you already have the PMOS transistor. So you can make this connection directly here itself. Is that logic okay? Oops. So again, let me repeat it. So what I'm saying is, you have, if you look at the extra branch we have added, we have a current source I0 by 2 and a PMOS transistor, right? Now if you look at the left branch we have here, we have the same guy, right? So instead of having a separate branch, we can reconfigure this branch in this way. So what I'm saying is this. So the NMOS has no change. At the PMOS, this is what we had originally, right? So what we want is to generate a bias voltage for this guy so that it carries a current I0 by 2. Here you already have the current I0 by 2, so we can basically do this. Is that okay? Because basically this branch here and this branch are basically same. I mean, I don't need to have a separate copy. I can kind of do this hack and obtain the required voltage. Okay. So this is, again, let me label the transistors M1, M2, M3, M4. The current is I0. Okay. So I mean, this is, we kind of thought this should work. So let's see if it works, right? So first of all, one thing to notice, the two circuits here, they are not exactly equal. This is a circuit we started with. We kind of tweak something to get here. They are not exactly identical. That is number one. So let's actually try to analyze if this indeed works properly. Okay. So for that, first let's try to find what will be the operating point voltages and currents. So what do you think will be the currents in the transistors M1, M2? Why is it same? Okay, so one important thing to notice, this circuit is asymmetrical. Okay, so here you see that both these guys are basically identical. You had a symmetrical case, so whatever current you have, that will split equally here. But that's no longer the case in the new circuit we have. Okay, so what can we say about the currents? Now, I mean, why is it same? I just told you can't use the symmetry argument.
VGS of both of them are same. I mean, they are like current level.
Yeah, okay. So here we are considering effect of R0, right? So the current is not only dependent on VGS, but also on VDS. Okay. So what he made is a good observation. The gate to source voltage of both these guys are same. I mean, for DC bias, both gates will be at the same voltage. Okay, so this will be at some VB, this will be at some VB. Right?
I'm talking about the M3 and M4.
Even for that, you don't know about this drain voltage yet, right? Okay, negative feedback is generating this voltage. Okay, so I mean, let's quickly check, right? So let's say the current through this transistor is I3, this is I4. First tell me what relation between I1 and I3. They will be same. Is that okay? Similarly, I2 is I4. At least that part is clear. Okay. So now, as we just saw, the currents through the transistors M1 and M2 depend both on the gate to source voltage, drain to source voltage. So gate to source voltage is fine, they are equal for the two. So only thing pending is the drain voltages here. Okay. So if I call it VD1 and VD2. So let's say what happens if VD1 is greater than VD2. So if VD1 is greater than VD2, which of these two will be higher? I1 will be higher because transistor M1 is at a higher drain to source voltage. Fine. But remember, this is also the drain voltage for M3 and M4. Okay. And for a PMOS transistor, if the drain voltage is higher, what will happen to the current? For a PMOS transistor, remember the current depends on source to drain voltage. Okay. So if the drain voltage is higher, current will decrease. So now you see that I have assumed VD1 to be greater than VD2. So what can you say about I3 and I4? Huh? So I3 is the current flowing through the transistor M3, and that seems to have a higher drain voltage compared to the transistor M4. So we just saw if for a PMOS, if the drain voltage is higher, the current is lower. So which means I3 is less than I4. Okay. But we just saw that I1 is equal to I3 and I2 is equal to I4. So this seems to imply that I1 is less than I2. Okay. So obviously there is a contradiction. So you definitely cannot have VD1 greater than VD2, and you can argue the same way if you say assume that VD1 is less than VD2. There's going to be no difference. Okay, I think it's the other way, right? A similar counter argument will hold good if you started assuming the other way around. So the only possible solution is VD1 must be equal to VD2. Okay. So then what can you say about the currents? All the currents are equal. Okay, so I1 is I2, and obviously this is I3 and I4. Is the logic okay? So what is this current equal to? I0 by 2, right? Okay. So this is how the currents actually become equal. Okay, the circuit is asymmetrical, but still you see that the only way to have a stable operating point is to have equal drain voltages for the transistors. Okay, great. So this is fine. So now can you tell me what will be the drain voltage of the transistor M1? That is this voltage which I am marking here. Yeah, basically this is, if I call this as the supply VDD, the voltage which I have marked here, this is the supply voltage minus the source to gate voltage of the transistor. Is that okay? So this is basically VDD minus source to gate voltage of the transistor M3 when it is operating at a current I0 by 2. Okay. This so will denote the gate to source voltages. I mean, of course, you know how to find gate to source voltage for a given current, right? I mean, what is, let's say, for an NMOS, what is the gate to source voltage in terms of the current? I mean, okay, guys, work it out. It will be something like this, right? Plus VTH. So instead of writing this complicated looking expression, we'll just say it like this. That's all. I just say what is the source to gate voltage or gate to source voltage and what is the current flowing in the transistor. With that you can actually calculate what is the exact voltage. Okay, and of course this is also equal to VD2. Fine? Yeah, current is I0 by 2. Sorry?
V over time is 2 times the current divided by it will be I0 by 2.
Okay, sorry. I mean, I just wrote for a general current. I mean, this is ID. Okay, sorry. is for a general transistor. This is ID. I think my handwriting is not great. If a transistor carries a current ID, I'm just saying this is a gate to source voltage, right? So, okay. So let me redraw the circuit here. So now we have established that the operating point currents are I0 by 2 if this current is I0. Let's quickly find out what will be the incremental gain. Okay. Again, let's assume V1, V2 here. And please note, we can't use all this business of half circuits here, because even if I apply a symmetrical input like this, where this side is plus delta V by 2 and minus delta V by 2, the circuit is not symmetrical. So we can't do any reductions in this. So no point in looking at half circuits. Let's directly assume that we have V1 and V2 and find what is the output. Okay, of course, one way is to do the small signal analysis and find. I'll leave that as an exercise to you guys to work out, so that you get some practice. But I'll take a different route to this. So we know that this guy is implementing something like this, right? Where this is a transconductance GM pushing a current through an output resistance. Okay, and let me mark it. So this is V1, V2 and V out. This is basically a model for this. That's all. Okay. So now here, what is the output V out in terms of V1 and V2? The current coming here is what? V1 minus V2 times R out. Okay. So the gain here is GM times R out. So if I know both GM and R out, I can actually find what is the gain of this circuit, right? And of course here, you know how to find R out. You just apply a test voltage and then find the current, blah blah blah. But how will I find GM here? Or here, first of all, how will I find GM? So let's say this is put in a black box and only these terminals are accessible. How can I measure GM? Huh? No, I can't hear. Can you be louder? Actually, cannot hear at all. Can you be louder? No, it's okay. Say if it's wrong, it's fine. What's the problem? Yeah, why? Okay, so what is short circuit current? How do you measure it? So he's saying that we'll short the thing here. So then you apply a voltage here. I mean, you already applied a voltage here. So what will be this current? Yeah. What will be this current? If I apply V1 and V2, the current coming out of this block is GM times V1 minus V2. Now if the output is shorted, where will this current flow? It will completely flow through the short circuit. So basically you can short circuit the output, measure what is the current flowing in, and then divided by the voltage, that gives the GM, right? This is the short circuit GM. Okay, so we'll do the same thing for our circuit also. Okay, so first we'll try to find what is the GM of this, that is the short circuit GM, and for that, like he suggested, we'll short the output. Okay, this is all small signal short. Okay, so let me draw the incremental thing here itself. So VDD is also a short here. The current source is open, so I'll basically take it out of the picture. So now this is the current we are interested in, and this current will arise both due to V1 and V2. So we'll again use superposition and find the contributions individually. So first let's find what is the contribution due to V1. Okay, so if I think about it, this is V1 This is a transistor M1, and looks like at the source there is some impedance here, right? So where is it? So what is the impedance looking here? 1 over GM, and please remember it's 1 over GM because the drain here is a short. So at the drain side the impedance is 0, right? So as we saw in the last class, only if you have a very small resistance at the drain, only then you can say that the impedance looking into the source is 1 over GM. So here I will replace it with 1 by GM2, okay? And I mean usually these two are identical transistors, M1 and M2, so I will say that this is also equal to GM1, okay? So what will be this voltage now? Vx. So what kind of configuration is this in now? Yeah, it's common drain, source follower configuration. So again, I asked you to check this, right? So if you have some RS here, apply Vi, what will be the output here? We saw it will be something like this, GMRS by 1 plus GMRS, okay? So here what is RS? That's 1 over GM. So what does it simplify to? 1 by 2, right? So basically Vx will be V1 by 2. So if I do the similar experiment with V2, that will again be V2 by 2. So the total Vx is going to be V1 plus V2 by 2. Let me probably write it separately. Okay. Again, please note this is equal to V1 plus V2 by 2 only in the experiment where we have shorted the drain. Okay. If you don't short it, this need not be equal to V1 plus V2 by 2. So only in this particular experiment where I have shorted the drain, this holds good. Okay. So now we know the source voltage. So what is the incremental current? Basically GM VGS, right? So this is basically GM V1 minus V2 by 2. So this current has no path to flow here. So where will it flow? It will flow into M2, right? It will flow like this. Okay, so I'll call this some I1. So I1 basically flows here. And here I have a short circuit. Obviously it will try to flow through short circuit I1. But mind you, the story doesn't end. So remember, this current I1 also flows through M3, right? And M3 and M4 is a current mirror. So whatever current is flowing into M3 will be copied onto M4. Okay, so what is the current flowing here? That is also I1. Is that okay? So what is the total current I out now? So I out is 2 times I1, and I1 we know is GM times V2 by 2. Okay, so this is basically GM times V1 minus V2. So what is the short circuit GM here? It's GM1. Let me mark the transistor name. It's GM1. Fine?
One question, intuitively we can say this way, the output voltage Vx is V1 plus V2 by 2. This is because this M3 is a diaphragmatic MOSFET that is having a resistance 1 by GM.
Okay.
That's a low impedance. So the drain of the M3 is a low impedance node, and this drain of input is low impedance node due to the ground.
Yeah.
So they are approximately symmetrical, approximately.
Yeah, that's exactly what we also got. Yeah, you're right. Yeah.
So in that sense, we can say this is V1 plus V2 by 2.
Yeah, exactly. I mean, what he's pointing out is, since we have shorted it, it looks like at this drain we have a low impedance. At here also, if you think about it, what is the impedance looking up? It has RDS, but also has a contribution due to the GM block, right? So we'll see it in probably I'll show it here. So you have a configuration like this, so let's say you apply a test voltage here to find the impedance. Okay, so between drain to source you obviously have GM VGS, also the R0 of the transistor. This is ground. So whatever you apply here at the drain is also applied to the gate. So the current, let me write it clearly, this is GM VGS. So if I were to measure the current IT, that is going to be what? What will be this current? It's GM VGS plus VT by R0. And what is gate to source voltage here? I mean gate to source is VT. Okay, so this is basically GM times VT plus VT by R0. So this VT into GM plus 1 by R0. So what is the effective resistance if this is IT? So this is basically a parallel combination of, okay, I mean remember this is basically the conductance, right? So I can also write it as GM plus GDS. Okay, so basically the conductances are getting added, so the resistances will be in parallel. So approximately this is at 1 by GM. Okay, so anytime you have a transistor whose gate and drain are connected, the looking in resistance is approximately 1 by GM all the time. Okay, great. So now we have found the short circuit GM. Let's find the output impedance quickly. Do you guys have class at 9 o'clock? If you don't have class at 9, can I take 5 minutes? Let me make it quickly. So to find output impedance, again what you have to do, you'll have to apply a test voltage here and measure what is the current coming, and I'll de-energize all the other inputs. That's all. Okay. So now in the incremental picture, current source is gone. I don't have to consider. The supply is a short. Fine. I'll quickly mark the transistors like this. So if this is the current I test, notice that it has two paths to flow, one up and down. So I call it I up and I down. Okay, so the test current IT is basically I up plus I down. Okay, so looking up, we have only the transistor M4, and in the incremental picture, M4 will have a GM VGS and R0, right? So basically I up will be basically the component due to GM VGS, which will come to later, and also the current flowing through R0. What is the current flowing through R0? VT by R0. I'll say R04. Okay, and let's quickly find what is I down. Remember, I down depends on what is the impedance looking down. Okay, and looking down, what do we have? Let's see. Here I have the transistor M2, and then something is connected to the source. And what is the impedance looking up? I mean, it can be 1 by GM provided the impedance at the drain side is small. And we just saw the impedance looking here is, it's 1 by GM because I have MOSFET whose drain and gate are connected. We just saw here, right? If you have a configuration like this, the impedance looking here is 1 by GM. So here also the impedance is 1 by GM. And for larger GM, this is a very small impedance. So looking into the source of M1, it is 1 by GM1. Okay. So at the source of M2, I seem to have a resistance 1 by GM1 connected. Okay, and this is the R down, the impedance looking down from the drain of M2. And this is remind you of some other configuration we saw now today. We have a transistor. To the source, I seem to have a resistor connected. It is basically the cascode configuration, right? So let's R down is basically the impedance connected at the bottom, which is 1 by GM1. This guy plus the R0 of the transistor you have, R02, plus the intrinsic gain of the transistor times the impedance connected. Okay, and GM1 and GM2 will be equal because the transistors are identical. So what does it simplify to? You have 2 R02 plus 1 by GM1, and for all practical reasons this is approximately 2 R02. Okay, so if this is R down, what is the current flowing down? Vt by this impedance, which is basically Vt by 2 R02. Okay, so this is basically Vt by 2 R02. Okay, so this is the current I down that will also flow here through the transistor M3. So this is I down, and remember, whatever current flows through M3 will also get mirrored onto M4, and that is this extra component we had here. Okay, so we already included the current flowing through the R0 of the transistor M4. In addition to it, you also have this current due to the GM VGS component, and that is basically this current mirroring action. So this is equal to I down. So the total current is what now? Okay, so what I meant was looking up, we had the current flowing through R04 and the current flowing through the GM VGS of the transistor M4. So this is the current flowing through R0, and we had something to be written here, right? And what we saw was the current I down that is flowing down, that actually flows through the transistor M3, that will get mirrored, and that mirrored current is basically this additional component. That's all. So what is the total current now? What is it? Basically Vt by R02 plus Vt by R04. Okay, so what is the impedance? It is basically the parallel combination of R02 and R04, right? So basically R out, I'll probably write it here, R02 parallel R04. Okay, so basically, I mean, you just have the current between these guys. So the short circuit GM we saw was GM1. The output impedance is R02 parallel R04. Okay, so for this guy, so short circuit GM was GM1, where these are the transistor numbers, and the output resistance was R02 parallel R04. So the total gain is GM1 times R02 parallel R04. Okay. So I mind you, I mean, the output resistance is a parallel combination of these two. So you might, just without looking into details, if you just see, you will think that if I look at the output, I seem to have these two guys, so that's how it comes in parallel, but that's not how it happens. Okay, because we saw that looking down, the resistance was not simply R02, it was something else. Okay, And other thing to notice is the gain here is GM times R02 parallel R04, whereas when we just had the old circuit where I just had two transistors like this, the gain we had was half of it, okay, and that happened because basically here you have two halves. Since we are taking output in only one half, we are discarding the other half. Currents were flowing in both the branches, but we kind of discarded one of the branches. But here what we are doing is, currents are flowing in both branches, but although the output is taken from one branch, the current flowing in this branch is mirrored back here. So that way we are reusing the currents and not wasting it, and that's why the gain is kind of double. Okay, so this is another way in which you can actually derive the same circuit. Okay, so I'll stop here. Overshot a lot.